Hey, this is Mr. Ayton. Welcome back, Pre-AP Chemistry. We are in Unit 12, a new unit of chemical equilibrium. And this is week 26. What are we going to take a look at in week 26? We're going to be looking at dynamic equilibrium. Dynamic means always changing. It's not static. It's going to be not in just one place, but the chemical reaction will be in dynamic equilibrium. We're going to be taking a look at particulate and graphical models of equilibrium, the Kc expression, and the magnitude of K. So let's get to what's called dynamic equilibrium. The definition for equilibrium is this, is chemical equilibrium in a reaction occurs when the concentration of the reactants and products remain the same. And also, chemical equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. It's not when the concentrations are equal to each other. It's when the concentrations stop changing, even though the reaction is still going back and forth, the concentrations of the reactants and products remain the same, and the rates of the forward reaction, how fast the reaction is going, forward and backwards, are going to be equal here, okay? Now, those two definitions didn't mean anything to you until you really look at it graphically and particulate-wise. So let's take a look at this reaction right here. This reaction is, we have hydrogen gas and iodine gas making 2HI gas. And you can see this little double arrow means that we are at chemical equilibrium. It's going back and forth. Not only is this reaction going forward, but it's also going backwards when it is at equilibrium. So how do we know when we're at equilibrium? Well, let's take a look at this first graph on the left-hand side. How do we know when we're at equilibrium? It's not when the concentrations are equal. It's when the concentrations stop changing. Do you see how right around here, actually it's probably a little bit further down, is right around here is right here, the reactants stop changing and the products stop changing. It doesn't mean there's not an exchange back and forth still. Remember, it's dynamically in equilibrium, but the concentrations are staying the same, which means the rates of the reactions are the same. By rate, you can take a look at the slope. You can see, take a look at the slope here. The slope here is very positive. The slope here is very negative. The slope here is less positive and less negative. The slope and the slope, once the slopes equal 0, they're equal to each other. That's the time at which we are at equilibrium. Let's take a look at this next graph. When would we be at equilibrium in this next graph? Right around right here or so. This is the time at which we're at equilibrium, because take a look. The concentrations stop changing. The concentrations stop changing. The rates of the forward reaction are equal to the rates of the reverse reaction. Now that's a graphical model. Let's take a look at particulate model. You can see in this reaction we have A producing B. This red is A, the blue is B. You can see how at the beginning, at time equals 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 particles of A and 0 particles of B. Well, guess what? That means the reaction is going to start shifting towards the right, towards the B. It's going to start producing B. You can see at time is equal to 1, what do we know at time is equal to 1? We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 particles, and now we have 2 particles. We're getting closer to equilibrium, but we're not there yet. Let's take a look at time is equal to 2. At time is equal to 2, we have 1, 2, 3, 4, 5, 6 particles and 4 particles. We don't know if we're at equilibrium yet. We might be at equilibrium. We're not quite sure. Let's take a look at time is equal to 3. Now we have 1, 2, 3, 4 particles and 6 particles. Oh, it means we're getting closer to equilibrium. And take a look at time is equal to 4. We're still at 4 particles of red, 6 particles of blue, which means time is equal to 3 is the first time when we are at equilibrium. You can see the concentrations are going to, from this point on, the concentrations are going to stay unless something from the outside has happened. Some sort of change has happened to my reaction at equilibrium. From this point on, we will be at chemical equilibrium with 4 red particles, 6 blue particles. It doesn't mean they're not exchanging back and forth. It means the concentrations are going to stay this same from this point on, and that means we are at equilibrium. Now we have also this thing called the K expression. That's the equilibrium constant expression, because constant begins with the letter K. So the equilibrium constant expression we put our products are going to go on the numerator here, and whatever the coefficient is going to be an exponent, And we're not going to add them, we're going to multiply them. And the reactants are going to go on the denominator here. You can see, again, the coefficient's going to go as an exponent, and we're not going to add them, we're going to multiply them in the K expression. Now, one big thing that you got to know for the K expression is do not put solids or liquids in your equilibrium expression. Why? Because they don't have concentrations. Okay, so do not put solids, do not put liquids in your equilibrium constant expression. So let's do some examples. Let's take a look at the equilibrium constant expression for this one. Do you see I'm going to put my products on the top, but do you see how I have a solid right here? So that doesn't go in my equilibrium expression. I have aqueous, so I'm going to put I2 right on the numerator, and I'm going to put it in brackets because brackets means concentration. Okay. Now, it had a coefficient of 1, so I don't really need to put an exponent. It's really an exponent of 1. On the denominator, I'm going to put my reactants. And do you see how I have copper plus 2, and you see I have 2 copper plus 2s. So that's going to be the concentration of copper plus 2 squared. Okay. Times, I have I minus, so I'm going to put I minus in brackets. And I have 4 of those, so that's going to be to the 4th power. And that is your K expression, Kc expression, or your K expression. Let's take a look at one more example for your K expression. This K expression, we're going to put our products on our numerator. So what's our product is NO2 gas, and there's 2 of them, so I'm going to put it squared. So again, don't put solids, don't put liquids in there, but put aqueous or put gases in there, okay, because those can have concentration. Now I'm going to go to my reactants. They're going to go in the denominator. So I'm going to put the concentration of NO, and there's 2 of them, so I'm going to square it, times the concentration of O2, and that's to the 1st power. And that would be my K expression for this reaction, for this equilibrium reaction. Okay? Now, the last thing we're going to take a look at is the magnitude of K, And if you know anything about math, this is going to be really easy. If your K is really big, if your K is a big number, what I mean by big is bigger than 1. That means your numerator is going to be very, very big, which means your products are going to be very high in concentration, aren't they? Which means if your K is above 1, you can see this is a ratio, the numerator is going to be bigger, which means the products are going to be what we call favored. But if the K is very small, what I mean, do I mean by small? I mean less than 1. So if the K is small, what does that mean about your ratio? That means your denominator is going to be bigger, isn't it? Your denominator is going to be bigger. You're going to have a number over a really big number in your denominator, which means your reactants are going to be favored. And so by the magnitude or the size of K, we can know what's going to be favored. So take a look at this first example. Take a look at this K value. This K is 5 times 10 to the negative 13th. That's 0.000000000005. It is a really, 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 really small number, which means if it's a small number, what's favored is your reactants are favored. Which means this will normally become a solid. If you put Ag plus and Br minus, think back to our precipitation reactions. If you put Ag plus and Br minus in a solution, it's going to make a solid. It's going to, at equilibrium, okay? It's not going to break up into positives and negatives. It's going to become a solid, an ionic solid, okay? So let's take a look at this second example. Take a look at this K. This K is really, 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 really big, isn't it? Okay, 2 times 10 to the 7th. That's 2,000,000,000. It's huge, which means what's going to be favored? Your products are going to be favored. Which means this substance is going to be way greater in concentration than your reactants, aren't they? If you take a look at a particle diagram, there's going to be a whole bunch of these AgNH3 pluses in your solution and very little of your other substances. Well, that is week 26, chemical equilibrium, unit 12, pre-AP chemistry. Yeah, boy. We'll we'll do some stuff in glass. All right, guys. Bye.